Okay. All right, so welcome to the Meow seminar. It's a pleasure to have Noah Fleming from Memorial University, and he will be talking to us about proofs and proof search or
Proofs.
problems.
Yeah,
And search
proofs in the
problems. Perfect.
covered screen.
Yes. Great.
Yeah. So this is going to be, thanks for having me and thanks for introducing me. Yes, this is going to be sort of a mix of a survey talk on connections between proofs and algorithms, and also some old work and some new work. I'll point out which those are. But yeah, hopefully by the end you take away that this connection between proof complexity and TFNP is interesting. Cool. Yeah, okay, so let me press, there we go. Yeah, so we're gonna start off with proof complexity. Probably a lot of people know this, but the main question in proof complexity is how difficult is it to prove a theorem? By theorem, we mean a propositional tautology, so we're only gonna focus on propositional logic, no quantifiers here. Really, maybe sort of implicitly talk about some later. Which is the same thing as proving the unsatisfiability of CNF formulas. Proof means in some propositional proof systems. So proof system is just like a sound and efficiently verifiable way to prove logical formulas. Sound means, you preserve satisfiability, you don't prove anything that's false, and efficiently verifiable means that there's like an algorithm that can check that your proof is actually correct in the size of the proof. And difficult is just going to be in the size of the proof. Typically, this is like the number of bits needed to write down the proof. So you've all seen resolutions, the standard example of a proof system. The goal is to derive the trivially false formula, the empty clause, which is falsified by every assignment, from your initial CNF formula by the following rule. So here's a CNF formula. We'll prove that it's unsatisfiable. And the resolution rule allows you to take two clauses with a complementary literal in it. So here you have clause C and D with complementary literals X and X bar, and you can derive their disjunction, canceling out the complementary literal. It's sound because any assignment either sets X to true or X to false, and so it only, it has to satisfy the other clause, so it satisfies the disjunction. Okay, so we can prove this formula. So we're allowed to derive new clauses from old ones. So here's the clauses. I've highlighted them. We can take these two clauses, derive Y. The complementary literal is X bar. These two derive Y bar and derive the empty clause from it. So very simple. So resolution is sound, which means that this is a proof that F was unsatisfiable. Okay, and throughout this talk, we're going to be, usually we measure proofs as like the complexity of proofs as just the size, which is in this case the number of clauses. We're going to use a sort of non-standard definition of complexity, which is logarithmic in the size plus the width, which is the maximum number of literals in any clause. This is not super important to focus on, but basically this is what allows us to get the connection to black box TFNP. So a proof is going to be efficient if the size is like polylogarithmic. We're going to say it's inefficient if it's more than that. Okay, yeah. So proof complexity says the complexity of proving tautologies in various proof systems, and I think 80–90% of my audience works in proof complexity in some sort. So maybe the why question is obvious, but for those of you who don't know, the original motivation was that if there's no proof system which has small proofs of every theorem, then P is different from NP. So this was one of the original approaches to attacking this problem. It's of course a very daunting task because there's infinitely many proof systems. How do you even start? So Kip Cook proposed this program building towards proving lower bounds on building toward this question by proving lower bounds on the size of proofs in successively stronger proof systems. Again, still very daunting, but this is at least an approach. So luckily, the size of proofs in specific proof systems is very intimately connected to the complexity of important algorithms. So these connections have seen consequences like CDCL algorithms, or the like CDCL SAT solvers, which are like the common algorithm for SAT, produce resolution proofs. Branch and cut integer programming solvers produce stabbing planes and cutting planes proofs. Grosvenor basis algorithms produce polynomial calculus proofs, and these Lasserre relaxations or sum of squares relaxations produce sum of squares proofs. There's also been connections between proof complexity and circuit complexity. So interpolation theorems turn, say, resolution proofs into monotone circuits, Shirley-Adams proofs into extended formulations, sum of squares proofs into SDP extended formulations, Mills-Dahlen-Satz proofs into monotone span programs. And in the other direction, we have things called lifting theorems, which turn, do the other direction. So if you have a monotone circuit, you can sort of turn it into a resolution proof. At a high level, this is what's happening. And these connections here have really revolutionized both areas. They've allowed us to get lower bounds, a ton of lower bounds in proof complexity and circuit complexity, faster algorithms and stuff like this. So all this to say is these connections between proofs and algorithms have been very, very fruitful, and they're worth studying. Okay, so at the heart of all of these connections is a deep connection to the study of total search problems. So kind of the intuition is that so a proof convinces somebody, a verifier, that a CNF formula is unsatisfiable. That is, for every input, the formula is false. Or more specifically, for every input, there's a falsified clause. Okay. So proving that a CNF formula is unsatisfiable is related to computing the following false clause search problem, which is very central to these connections between proofs and algorithms. So the false clause search problem is you're given as input a truth assignment to your unsatisfiable CNF formula F, and you want to output the index of a clause which is falsified by that assignment. So this is what is known as a total search problem, because for every input, there is a valid solution. The CNF formula is unsatisfiable, so there's always going to be a falsified clause. Okay, yeah, so in this talk, we're going to bring together two areas, proof complexity and total search problems. We'll see its consequences, explore its limits, and some cool things we'll see from it is a generic interpolation theorem, sort of roadmaps for lifting theorems, proof systems for total functions in the polynomial hierarchy, and maybe a little bit on how we can connect to white box TFNP if we have time. Okay, so we'll start off with total search problems. So for those of you in photography, I'm gonna kind of botch a few things here. This is a motivating example, not a realistic example. Okay, so a hash function is something that maps like n bit messages to m bit messages where m's less than n. So you can think about it like this. Here's the messages. Here's the things that it maps to. And so for security and usability, we want that it's generally difficult to witness a compression, or witness that this is a compression, find like a collision between two things that hash to the same thing. That is, we want the following problem to be hard, which is the weak pigeonhole problem. You're given as input a circuit which maps n-bit messages to m-bit messages, and you want to find a collision. So hash functions are used all over the place in cryptography, statistically hiding commitments, verifiable delegation, security, complexity theory, so on and so forth. Natural question is, how can we get evidence that this pigeon problem is difficult? We can't rely on NP hardness because this pigeon problem is a search problem, a total search problem. So you want to, it's not a decision problem, right? So decision problem would be like, does there exist a collision? In which case it could always output yes. It's total. You actually want to output the collision. Yeah, so it's a total search problem, which means search problem means that there's potentially multiple valid outputs for a single input. So you can see one is in fuchsia, one's in blue here. You could output either of these two pairs. So for example, see the search stat problem, output a satisfying assignment to a given CNF formula. This is a search problem. And it's total, so every input has an output. So search stat is not total because there are unsatisfiable CNF formulas. And so there's a ton of very important total search problems, such as integer vectoring, Nash equilibria, finding this Brouwer's fixed point, lossy code. These sorts of things have been popping up in a lot of recent exciting work. So in the late 80s, it was introduced this theory of NP for total search problems called TFNP. So TFNP contains all total verifiable search problems. So verifiable is like the NP definition of verifiable. Yeah, so a total search problem where we think of, so we write it as a relation. We'll think of the first input to the relation as being the input to the problem. The second input as being the output. It's in TFNP if there's a polynomial time verifier, which given an input and a solution, checks whether that is a valid solution to the problem. So for example, pigeon is in TFNP. So this is the pigeon problem rather than the weak pigeon problem. The only difference is that now the size of the domain is one more than the size of the range. It's slightly stronger. And so you want to output a collision again. This is in TFNP because given a potential solution, you just run the circuit on both of them and see if they map to the same place. So that's clearly polynomial time. Okay, so unlike NP, TFNP is not believed to have complete problems. It's kind of the search problem version of NP intersect co-NP. So because of this, you want to study subclasses of total search problems which do have complete problems, and then try to relate them. This is kind of the goal of TFNP. So these subclasses are typically defined by reduction to some complete problem. These complete problems are usually like existence principles, such as, if you have a map of too many things to too few things, there's a collision. This existence problem guarantees totality. So for example, yeah, pigeon is the complete problem for the class PPP. So you take the pigeon problem, you look at everything that's polytime reducible to PPP. This gives you, or to pigeon, this gives you PPP. And this is like the, it was one of the original TFNP classes, and it's kind of like the crypto TFNP class. It captures things like finding collisions, hash functions, variants of discrete log, lattice problems. There's also the iteration problem, which is characterized by the principle that says that like every DAG has a sink. So you're given as input a circuit. Essentially, it's going to define a path in a DAG. That's how you should think about it. So the input, there's 2 to the n vertices. So you should think of the domain of the circuit as being vertices in a graph. And you want to output one of the following things. So the circuit here you should think of defining edges. Each vertex has one outgoing edge, and you're given that one is like the root of your DAG. You always have to point forward, and you want to find a sink. So you want to output either a sink or a violation to one of the 2 previous conditions. So the first violation is that the vertex 1 is not a valid source. So that is 1 points to itself. We don't want that. The second one is something points backwards. You always want to be going down the DAG. Again, you could arrange these vertices in like a DAG structure, and this is why it's called sink of DAG. We'll see that in a minute, actually. Or finally, a sink. So a sink is defined a little bit weird, basically just to make it simple to write down. So we want to be able to turn off vertices, essentially. So we're going to allow them to self-loop. So if like, say, 5 pointed to 5 and nothing pointed to 5, you'd think of this as like a vertex that is like turned off or like isolated or something like that, not important. So then a sink for us is just going to be a vertex that points to another vertex which self-loops. So there's always going to be a sink in, like if you don't satisfy one, if like one is not a solution, then there's always going to be a sink because one points somewhere, which then has to point somewhere, or self-loop, and so eventually you find a sink. So it's a total search problem. And the class PLS is everything reducible to this iteration problem. It contains problems related to finding like local optima. Okay. So I've talked about, I said polytime reductions, but what does a reduction mean in this world? So we're talking about search problems, like, so we have to talk about mapping solutions to solutions. Decision problems, you know, the output was either 0 or 1. So a reduction to total search problems like R reduces to Q if there are polytime computable functions, F and G, such that the following condition holds. I can show you what this means in a picture, which is much easier than reading the thing. So these, no, okay. These should be named. The first one should be R, the second one should be Q. So just map those on visually. But yeah, so you're given an input to P here. F maps this input to an input to R. You solve R to get a solution, and then you map it back with G to P. And this is all it's saying, that if I solve, in this case R, I get a solution that I can map this back to a valid solution to P. Okay, so these are kind of the main TFNP subclasses. You've seen PLS and PPP. There's a few other ones. And the goal is to understand how these classes relate. Just like in standard complexity, you know, we have a bunch of classes, and we want to understand what their structure is. However, separation between any pair of classes would imply that P is different from NP. So that's, you know, a little daunting. So the main way that people have gone about trying to understand how these classes relate is via studying them in like the black box or Oracle model as a proxy, right? So in each of the TFNP problems I defined for you, the input is a circuit telling you something. In the black box model, you treat the circuit as an oracle. You're only allowed to ask questions to the circuit. You're not allowed to see what the circuit looks like. Okay. And it turns out that this black box TFNP is just proof complexity in disguise. So that's great for us. For people who only want to think about proof complexity, it's nice when things turn out to just be proof complexity. Okay, so TFNP proof complexity. Yeah, so as I mentioned, this black box TFNP or query TFNP, you're only given Oracle access to the input circuit. You can't see how it's defined. So for example, here's an instance of this pigeon problem, maps 4 things to 3 things. And we can think about a computation here. So you're trying to solve this pigeon problem. And so I'm going to try to reduce how we can study about this query, how we can study this query TFNP to talking about decision trees. So that's what I will do here. So let's fix an instance of the pigeon problem, 4 pigeons. And initially, you know nothing about the problem. Then you can do your Turing machine can do some like polytime computation. Still knows nothing about the input. Hasn't queried H. And then maybe it does a query to H. So it asks, where does pigeon 2 fly? Let's go down the branch where it flies to hole 1. So pigeon 2 went to the first hole. And then we do some more polytime computation. Ask about maybe pigeon 1. And it goes there. We found a solution if we went down the branch where it went to H1. More generally, you get this big thing that looks like a decision tree. And so what we can do is basically, we want to get lower bounds on the computation time of solving this pigeon problem. a lower bound on the number of queries gives us a lower bound on the total runtime. So we can just focus on that. That's simplify the model. So yeah, lower bounds on number of queries imply lower bounds on runtime. So we're going to study basically the number of queries that you need to the defining circuit in order to compute these total search. Okay, so typically when we talk about efficiency, we want the runtime to be polynomial. We're going to reparameterize things here, which will make things a little bit easier. We'll also relate back to this complexity notion for a proof system that I mentioned at the start. So 2 to the n was the number of potential queries. This is like the number of pigeons. It's encoded as a circuit, so there's only n input bits, but it encodes 2 to the n many things. So we're going to let capital N be 2 to the n. Then efficient means polynomial in n, which is polylogarithmic in capital N. So here, what we're asking about is like the decision tree complexity of these problems, where efficient means polylogarithmic depth decision trees. Okay. So black box TFNP is same as TFNP, except for now, rather than requiring that the verifier be a polynomial time Turing machine, we want the verifier to be a polylogarithmic depth decision tree. In particular, so a search problem is in black box TFNP if for every potential output, so 0, 1 to the n is the input and O is a set of potential outputs, we want a decision tree of polylogarithmic depth for each solution, such that X and O is a solution, like O is a valid solution to the problem on input X, if and only if the decision tree on input X for O outputs 1. Okay. So basically just saying our verifier can be computed by a low depth decision tree. And so we can also define a reduction in black box TFNP. It's the same thing as reductions in the regular world, except for now the functions have to be computed by low depth decision trees rather than polynomial time Turing machines. Yeah, so exactly the same definition before. R reduces to a problem Q. We're going to want the input size of Q to only be, sorry, this should be quasi-polynomial actually. We don't want it to grow too much, so we want the input size to be quasi-polynomial in the input size of R. And yeah, then we just have the standard reduction definition that we can take an input to R, turn it into an input to Q using low depth decision trees, solve it, get a solution O, and then turn it back using a low depth decision tree into a solution to R.
You can blow up to quasi-polynomial.
Yeah. The T here should be quasi-polynomial.
Okay.
And yeah, you can basically just like, if you allow it to be arbitrary, you can sort of cheat. You can encode too much information. So, yeah. Yeah, so we want each bit to be computed by a polylog and depth decision tree. Yeah. Okay. So then our goal again is to understand how these TFNP classes relate. Now we're going to try to do it in the black box model and hope that that is representative of the white box model. Okay, the main technique for doing this is proof complexity. So if you remember at the start, I talked about this false clause search problem. Given an input to an unsatisfiable CNF formula, output the index of a falsified clause. This is a problem in black box TFNP if F has polylogarithmic width. You can see this because to check whether a clause is falsified under assignment, you have to check basically the width of that clause. So if the width is polylog, you can do that polylog with n many queries, and so it's in TFNP. Okay. And this is just what I said. Yeah, so you check the variables in the clause, see if it's false. Since this false clause search problem is very related to proof complexity, and it's in TFNP, this means that roughly that TFNP should be important for understanding proof complexity. However, on the other hand, understanding proof complexity is crucial for understanding at least this black box TFNP. So the intuition is really that like a reduction between two total search problems is a proof that one total search problem or what one search problem is total, assuming the totality of the other. This is how you kind of get proofs out of this. So a proof is going to be a reduction between total search problems. And so you're reducing like a problem P to a problem Q. P will be like will turn out to be your unsatisfiable CNF formula. The reduction will be your proof, and Q will be like the reasoning power of your proof system. So the proof system can basically prove reductions to Q. That's what we'll see in a second. Yeah, and what we're going to show is we get very nice characterizations out of this relationship, that certain black box TFNP classes are equivalent to the tautologies that are efficiently provable in certain proof systems. So you can reduce to that. You can prove membership. Sorry, you're a member of a TFNP class if and only if a corresponding proof system can prove the totality of that search problem. Okay. So the reason that this happens, the reason really that you get this connection to proof complexity is that sort of for TFNP, you can, in the black box world, you can really forget about the particular total search problems you're working with and just focus on the false clause search problem. So everything can be rephrased as this false clause search problem. That's what this claim is saying. And the idea is to take a TFNP problem and encode it as a unsatisfiable CNF formula, which asserts that the total search problem is not total. So it's going to be unsatisfiable because we started with a total search problem. This is not too hard to do. So let's start with a total search problem. Because it's in black box TFNP, there are low depth decision trees that are verifying like solutions for it. This is just the definition. And so we're going to encode, we want to write down that R is not total. So first thing we're going to write down is that, we'll do this in steps. So first thing, we're going to write down a small propositional formula that says that for a fixed solution O, that it's a solution. So we can use these low depth decision trees in order to do that. So here's one of these verifying decision trees. On input X, TO will output 1 if and only if O is a solution on input X, and it'll output 0 otherwise. It's just like a little verify. We can view paths in a decision tree as a conjunct, right? So like at each step in a decision tree, you query a variable. If you set to 1, you add that variable. If you set to 0, you add the negation of that variable. This gives you a conjunct. Paths in decision trees are conjuncts, and we can write down that O is a solution, like a formula that asserts this, by taking a big OR over all paths, which would make the decision tree output 1. Okay. And then using this, we can just say that R is not total. So we say, we take a big AND over the negation of these DOs. So basically we say for each solution, for each potential solution, it's not actually a solution. And so that's what the formula asserts. And now you can see that that you get a false clause to this, like a falsified clause to this formula is the same thing as a solution to the original search problem R. So yeah, so a falsified clause means that some clause of one of these DOs is satisfied, and hence the solution, that's a valid solution on X. Yeah. And
okay.
Yeah, and please interrupt me if you have questions and stuff.
So just to make sure, is the definition of TFNP, do you need that the tree can verify some outputs for every X, or does it have to verify all the possible, like if O is a valid output for X?
So we have one tree for each output. Perhaps this is what you're asking.
You have one tree for each output, and that tree, because it's an if and only if there, right? So that tree must be able to verify all the X's. So if there's one particular X for which O is a valid solution, but for this X, you would need to has a very large certificate, let's say. So you need to query a lot of things. That wouldn't be in TFNP. Even if like you can verify another output for this X.
Yeah, no, you have to verify every possible solution. Yes. Okay. Yeah. That's a good question. Okay. Yeah. So for what Susanna was asking is like you could think of like a CNF formula where some of the clauses are very large and some of the clauses are very small.
Maybe you don't need
the large clauses. Could you only verify the small ones? No, you actually have to verify like every potential solution. Yeah. Okay. Yeah, that's a good question.
So this formula would be like quasi-polynomial?
Yeah, exactly. Yeah, that's something I should mention. So the formula has quasi-polynomial size, and each clause is polylogarithmic, at most polylogarithmic width. And that's because each of these decision trees has polylogarithmic depth, and you're taking like an and or an or for their paths. So you get, polylogarithmic width and quasi-polynomial size. And usually when talking about connection between proof complexity and TFNP, quasi-polynomial is going to be roughly quasi-polynomial size is roughly our measure of efficiency. There's arguments that in proof complexity, maybe this is the right notion of size, but so this shows that black box TFNP is exactly the false clause search problem. We only need to study this thing. Okay.
And I got a little bit confused by the slide, but what we're trying to say, we just have a big and over all possible answers.
And we're saying that's not an answer.
A big and for each O, we have a big and overall one path, and then we just say that some variable or some literal on this path takes the wrong value.
Yeah. We're just saying like for every possible solution, that's not actually a solution. Yeah, so for every one path, we don't follow that one path. Yeah. Just saw this. Okay, so this leads us to characterizations of proof systems. So the really neat thing that comes out of this is like that certain proof systems, like provability in certain proof systems, is exactly membership in certain classes. This is really nice, obviously, for TFNP, but it also turns out to be very nice for proof complexity, and you can get some very neat results out of it, which I'll talk about in a second. So we're going to say that a proof system characterizes a class C if for all search problems R, the proof system has a short proof of the associated formula that we just constructed, if and only if R is in this class.
And sorry for nagging you. By short, do you mean short and somewhat narrow?
Yes, good. Yeah, so I will use terms like short and small, and I'll be very loose with them. But they all mean polylogarithmic complexity, which means, yes, and this is actually a good time to mention this. So it means like quasi-polynomial size and I guess quasi-polynomial size and polylogarithmic, say, width. It becomes this. One of the reasons I didn't want to get too into this is that width is not so well defined for each proof system. Like for most of the proof systems that we have studied, there's a natural width or degree notion, and we'll just assume that that's one that that's the one that we'll use. So, for example, like if you know like Shirley atoms or something like that, width will be degree. For resolution, width is width. For res k, width is like bottom fan-in width. You can actually standardize this and show that, I guess, for any proof system for which this characterization stuff holds, there is a natural notion of width, and I will prove this a little bit later in the talk. But yeah.
Does this natural notion of width have anything to do with proof search?
Yes.
Yeah.
Well,
or not necessarily?
Proof like verifiability. Basically, you just need to
verifiability.
be able to check like
Okay.
a violation in the proof.
Okay.
In all these characterizations, what you're really going to do is like write down, encode the proof in such a way that it can be solved by a TFNP problem.
Okay.
And so you need to be able to check. The TFNP problem is going to be looking for a violation of the proof. And so you need to be able to check this violation by a small depth decision tree.
Okay.
And however you encode it gives you this little like notion of width, which is basically just like, what's the information I need to check the violation?
Okay.
Yeah.
Okay.
Yeah, good question. Hopefully clarified it. And yeah, if you have any more questions, please interrupt me. Okay, so one of the really surprising things that come out of this is that so TFNP and proof complexity were studied really separately at the start, at least. And surprisingly, like almost every TFNP class that was introduced naturally corresponds to a proof system that was introduced independently and very naturally. So you get this like really converging of two worlds in a way that is like bizarre and kind of makes you think about like how do people reason about things, I guess, like philosophically. Anyway, so here's the TFNP classes, and here are the characterizations we know of. So PLS, this sync of DAG thing is resolution. PPADS is Shirley atoms. You get things for Null-Stullen sets, tree-like resolution, and you can get them for a lot of other proof systems, but I'm just mentioning the major classes here. Okay, so I want to give you an idea sort of how one of these characterizations works. And we'll prove in the second half, we'll actually prove a characterization in full related to this range avoidance problem in TF sigma 2, which has been kind of exciting recently. Okay, so we want to show that resolution characterizes PLS. That is, we have a small, low complexity resolution proof if and only if there is a like the corresponding search problem is in PLS. Okay, so here's the resolution proof we had from the start. And remember, PLS is the problem of finding a sink in a DAG. So we're going to introduce one vertex for every one of the clauses in our proof. And for all the axioms, like the clauses belonging to F, we'll just self-loop them. So these will be like, essentially what we're setting these up to be is potential solutions. Our goal is to find a falsified clause, this thing. So then for each non-axiom, what we're going to do is either that line was satisfied under the given assignment, in which case we'll just self-loop it, or we'll point it to its falsified child. So you've probably seen this a bunch if you've worked in proof complexity, these sort of strategies for proving depth lower bounds or something. You start at the root, which you know is always false, and you walk to the falsified child. And this is just what we're doing here. So for example, here, the decision tree for vertex 2 corresponding to the class y is going to query y, and then if y is satisfied, it'll self-loop, and otherwise it'll query the variables in its two children and point to the one that is falsified. Because the proof is sound, at least one of the two children is going to be false. Okay, so let's suppose we have this assignment, 0, 1, and so y is set to 1, so we self-loop it. So under this assignment 0, 1, like the root, the empty clause queries y and points to the child that's falsified, which is y bar. So we get this edge, and then y bar queries x and y and points to the falsified child, which is 6. And you can see that this corresponding clause is falsified under this assignment. So this solves the falsified search problem associated with this one. Okay, so that's one direction of it. The other direction is a little bit more complicated. Again, I'll prove a formal characterization later. If you know the delayer prover game, you can prove it very nicely through that. But doing it directly with resolution takes a bit of work.
An extremely stupid question. Please remind me what PLS is.
So that's like complete problem is finding like the sync of a DAG or iteration. So you're given it's a bunch of different ways to define it, but like think of
the definition you had before, I think was good.
Yeah.
But where was the sync in the proof then?
Where's the
sync? Go to the definition, I think.
Yeah, okay.
that explains what the definition of sync is.
It's maybe a ways back.
Oh,
No worries. Hope I didn't miss it. Yeah, here we go. Yeah. So this is iteration. So you're given, so it's the principle of finding a sync and a DAG, but we can just think of it like topologically number the vertices in a DAG. We want that 1 is like the root of the DAG. 1 should point somewhere that's not itself. We're going to say that a vertex like self-loops. It's like if a vertex self-loops, it's like not included in the DAG. So we want 1 to point somewhere, since the root should point to something, and we're trying to find a sync. So since it's a DAG, you should always point forward. That's the second solution. So violation to that, you could output. And then finally is a sync. So sync is defined as a vertex that points to another vertex that self-loops.
Okay.
Yeah. Just. Okay, so some upshots of these nice characterizations. First is that proof complexity lower bounds can be used to prove black box separations between these TFNP classes. This has resulted in a complete picture of the relationships between the major TFNP classes. It also gives very nice structural results for proof complexity, such as we get like combinatorial complete theorems for complete problems for proof systems. So previously, like for some proof systems, the reflection principle was their complete problem. And now you get much nicer things. By complete theorem, I mean you can simulate the proof system essentially if and only if you can prove this theorem. So you get that resolution is pebbling, Null-Stalled over F2 is Citon, Shirali-Adams is injective pigeonhole. You get things for polynomial calculus and Null-Stalled over other fields. You get separations between large and small coefficient proof systems. This was a very nice result. Intersections between proof systems, which is a surprising thing. Very natural to talk about like the intersection of two complexity classes, and you can use this in the characterization idea in order to talk about intersections between provability and proof systems. And you get new proof systems from this. Like you can take a TFNP problem and generate a proof system out of it. And sometimes these proof systems turn out to be sort of natural.
Can I
Yeah.
ask again? Sorry. So for instance, the second bullet, this complete theorem thing. So you're saying like my proof system. Do I understand correctly that my proof system can simulate resolution in whatever efficient simulation sets we have, if you can do small polylogarithmic with
Yes.
proofs of unsatisfiability?
You also need to be
formulas.
closed under decision tree reductions, which is a small caveat. So if you have, I'll talk about that in a little bit, but like basically if you have a decision tree reduction to the false clause search problem for some unsatisfiable CNF formula, this gives you sort of by sticking in that reduction into the CNF formula, gives you a new CNF. And you want to say that if I could prove the original CNF and the reduction was efficient, I can prove the reduced thing. If you have this plus the complete problem, then yes.
And because you're plugging in the decision, that's like where small width is somewhat important, because
Yes.
otherwise your blow up would be terrible.
Exactly. Yeah. Because if you compose like
So
if you stick a small decision
somewhat
tree in,
counterintuitive, like for instance, all pebbling formulas are very easy for tree-like resolution, right? Except that the proofs go very wide. So I guess that's why.
Yeah.
That's what's wrong there.
Yeah. Okay. So I showed you characterizations or put names to TFNP classes here, and these were all the major TFNP classes. And you notice that there was one that was missing, this PPP class. This will bring us to like an open problem that I have that's been bugging me for a while, which is whether there's a natural proof system for PPP. We have all these TFNP classes. We have characterizations of some of them. You could ask, like, can we sort of mechanize these characterizations? Is there like a black box, I guess, way of like, given a TFNP class, does it just produce a proof system in some way that I don't need to think about? Like all of the proofs so far have been very ad hoc. Can we just like, is there just a machine I can throw at it and it produces the proof system? And like questions like these classes that we don't have proof systems for, are there proof systems for them? Have we just been like bad at thinking about them? Or is there some reason that there's no proof system? So first question is whether every TFNP subclass has a characterizing proof system. The answer to this we showed is yes. I'll show you how to do that at the end. And also, does every proof system have a characterizing subclass? And here the answer is they need to be able to prove the soundness, like prove their own soundness in a way. So they need to prove what is known as a reflection principle about itself. The reflection principle turns into the complete problem for the TFNP class, and we get a characterization through this. There's slight caveats to this.
Infinitely.
Yes. I think it should be.
Okay.
Yeah.
Because for resolution, like these weak proofs.
Yeah. So I'll talk about what a reflection principle is. Yes.
Okay.
Good. So you need the reflection principle to be efficiently verifiable. So there are ways to write down the reflection principle such that they are and such that they are not.
Okay.
And I think the reason that this doesn't run into issues like Atzerius-Müller, things like that, is that we're talking about low width resolution here. We have this notion of complexity, which corresponds to basically polylogarithmic width resolution proofs, and those can prove their own reflection principle.
So resolution only has to prove the reflection proof for low width resolution.
Yes. Okay. Exactly. Okay, and from this, we're going to get a generic interpolation theorem, and we can use this to talk about like a roadmap for lifting theorems. Interpolation theorem converts proofs to circuits, and lifting theorems convert circuits to proofs. So I had this question: does PPP? So we showed that PPP has a proof system, just by this previous result. This proof system is going to be sort of cheating. It's going to be reductions to PPP, not a very satisfying answer because like nobody would study reductions to PPP as a proof system from the perspective of proof complexity. So a question that I'd like to know the answer to is whether PPP has a natural proof system, which is like a proof system that you would ever come up with if you just studied proof complexity. One observation is that every class that we have a characterization for is closed under Turing reductions. You know, in like a standard reduction, you turn an instance of your problem to an instance of the problem you're reducing to, and then back. You're allowed one call to the instance of the problem you're reducing to. A Turing reduction allows you many calls to it. So in every class that we have a characterization, standard reductions are the same as Turing reductions. You can always just kind of fold the Turing reduction in. Okay. And a conjecture that I'd like to know the answer to is, does for a TFNP class to be characterized by a natural proof system, don't have a great definition. This is sort of a definitional problem. But does it have to be closed under Turing reductions? Can I say if a TFNP class is not closed under Turing reductions, then the proof system you're going to get out of it is like artificial in some way? So this was one of the original motivations for us trying to show that PPP is not Turing closed in the black box setting. So if you can resolve this conjecture, then this shows that PPP should not have a natural proof system. Yeah, and I'll say one word on the proof of this, which I think is just kind of a cool tidbit about like so the way we prove this, we separate PPP from the Turing closure of PPP. So like you take Pigeon, you allow Turing reductions to it rather than regular reductions. So you have these two classes, the Turing closure of PPP and PPP. And the way we prove this is we build a new proof system which lies in between it. And we show that this proof system can prove everything in PPP. And there's things in the Turing closure that it cannot prove. So it's a proof complexity.
Is this a natural proof system?
Yes, it actually is, which is even more annoying. Yeah, you know, it's natural enough. It's like an extension of Shirley Adams. Yeah, it's like sort of related to Markov's inequality, maybe with unary weights. But yeah. Yeah, so you know, we showed that the PPP does have a proof system. However, this proof system that we get is not so natural. It's just reductions to the Pigeon principle. Oop. Okay. Okay, so I think this is about an hour, and I'm also exactly halfway through my slide. So maybe we can take a break. And the second part, I'll tell you about how these connections between proofs and algorithms come up, and then also talk about things beyond NP. Yeah, and do some characterizations and stuff.
Okay, thank you. Are there any questions so far?
Yeah.
So do we have like any idea whether we can get a proof system for the full T?
It doesn't have, we think it doesn't have complete problems, and you need to have a complete problem in order to get a proof system characterization. So
But TFNP
probably
DT has a complete problem.
no,
No.
because the search problem is what you're actually getting is a strat, like you get one search problem for each false, like unsatisfiable CNF formula.
Okay.
Yeah, so you're getting many.
Okay.
Yeah. Yeah. If there's a way to turn it into like the input is also the CNF formula, but then it becomes a promise problem.
Oh, okay.
The question is, do we expect there to be some kind of hierarchy with stronger and stronger complete problems to be below TFNP. Like if you
Oh.
have your lattice that you showed,
Mhm.
like there are maybe things between the pigeon and
Yeah. So you can. Sorry, are you asking if there's like
An
a
infinite,
lot? Oh, sorry.
is there an infinite number of classes between?
Yeah, I think so. You can probably always just come up with like an infinite,
Because these GF classes, do they lie?
like the GI.
GI classes, sorry, graph,
Oh,
the
oh,
graph, or do they lie in between, or
You mean the like
what are these classes? Those ones.
game induction things? Is that
Yeah.
what you're talking about?
Mhm.
Depends on how you define them.
Okay.
I think if you Herbendize them, then yeah, you're gonna. Yeah, that's a good answer. If I'm remembering, maybe the game induction things are already Herbendized. But yeah, I think there's ways to construct like infinite things that we at least we believe are all different.
Right, of course, yeah.
Yeah,
Okay.
but I mean, you can probably separate. You separate? No, I think this is asking whether you can separate D and D plus one.
If you
Right
could.
up. Yeah.
Okay.
Thank you.
Okay, now we are back after the break.
I'm a little
Sorry about
further.
Is the recording running really?
The recording was running, but it wasn't the video and so only the slides were being recorded, but not the sound, I think. Yeah, because I had turned it off during the break. Sorry about that. Okay, so now they can hear you.
Great. Yeah. So there's this, result, the Karchmer-Wigderson result, which shows that like the monotone formula size is equal to the communication complexity of computing the following relation, which is called the monotone Karchmer-Wigderson game. So you're given as input a 1 of the function and a 0 of the function. Function's monotone, and you want to output the index of a bit in the 1 part, the 1 of the function, which is greater than the same bit in the 0 part. This is total because f is monotone. Okay. Oh yeah, the size are off by a logarithmic factor. So you can really reinterpret this result as saying that the class FP, which is like functional P, or like the corresponding class for P in TFNP, the FP, when you're doing reductions using small communication protocols, is characterized by monotone formulas. Then this was later extended by Razborov, who showed that monotone circuits are characterized by PLS with communication reductions. So this leads us to like a theory of communication TFNP. Rather than using decision trees, we're going to use communication protocols. Everything else is the same. So we do have to split the variables of the search problem we're computing into 2 sets, and for them to be amenable to like a communication protocol. But yeah, so a total search problem is in communication TFNP. If for every solution you can verify, there's a small communication protocol verifying it. And we get characterizations from this that certain subclasses of communication TFNP are equivalent to functions computed in monotone models of computation. And this is all just analogous to the black box TFNP world. And just like how the false clause search problem was like a complete problem, or like a way to like kind of uniformly view black box TFNP, the monotone Karshmer-Wigderson game is the same for communication TFNP. So communication TFNP is the study of the monotone Karshmer-Wigderson game. And from this, we get a bunch of characterizations. I just mentioned PLS is circuits, P is formulas. We also get extended formulations, span programs. These are monotone span programs over F2 and Z.
Everything here is monotone, right?
Yes. Yeah. So these are all monotone. Okay. And so this gives us sort of a roadmap to these lifting and interpolation theorems, which connect circuit models to proof systems. And why is this? Well, every time we've had like a characterization of the black box in the communication world, we've gotten a lifting theorem between and an interpolation theorem between the corresponding models. So the first example was, it's kind of a folklore result that communication protocols can simulate decision trees. Pretty easy. In the other direction, Ross and McKenzie showed that there's a lifting theorem which transforms monotone formulas into decision trees. Similarly, we have this for resolution proofs and monotone circuits. This is the result of GGKS. And in fact, we have a lifting theorem and interpolation theorem between every single one of these classes. So every time we have a characterization of the black box and communication versions of a TFNP class, we've found a lifting theorem and interpolation theorem between the 2 things. Which suggests that these characterizations can tell us when we should expect these very useful theorems. So the question is, why is this happening? So we can answer this question for interpolation. There's actually just kind of definitionally, you get a generic interpolation theorem. So if you have a TFNP class and you have a characterization of the black box version by a proof system, and a characterization of the communication version by a monotone circuit model, then you immediately get an interpolation theorem turning proofs in the proof system into circuits. Yeah, and so you can use that. You can combine this with the earlier result I mentioned, that like basically every proof system that can prove its own reflection principle has a characterizing TFNP class to get a generic interpolation theorem for all of these proof systems. Okay, and the intuition behind this is it's extremely simple. Basically, the communication protocols can simulate decision trees. That's all you have to do. So I'll prove it to you now. Okay, so the proof is simple. Let's consider the false clause search problem let's consider the false clause search problem in this class, like some TFNP problem in the black box version of this class for the CNF formula being this. So we have M clauses, and by some earlier results, we know that you can take the false clause search problem and turn it into a partial monotone function, such that a solution to the Karchmer-Wigderson game on this monotone function is a solution to the false clause search problem. So now let's take a complete problem for the class C. And so if the proof system proves a unsatisfiable CNF formula F, then the false clause search problem reduces to this is because of the characterization here. So since the proof system is characterized by the class C, and the proof system proves F, then the false clause search problem reduces to complete problem in that class. Then because, so this is a decision tree reduction, any decision tree reduction is also a communication protocol, or a communication reduction, because decision trees are a restricted form of a communication protocol. So we get the monotone Karchmer-Wigderson game communication reduces to R. And so because we have this characterization of the communication version of this class by the computation model M, we get that M computes this corresponding function. So this is very simple interpolation theorem that just comes out of having these characterizations. Okay, so we say the same thing for lifting. So unfortunately, there's no generic lifting theorem. Would be very nice. However, as I mentioned, like all query communication lifting theorems with the index guide are kind of like captured by this framework, at least to my knowledge. So this suggests that at least this is a good roadmap for this. Okay. So that's all I'm going to say about these connections between proofs and circuits. Next part, I wanted to talk about some very recent work, brings us up to 2025, with my PhD students on characterizing things beyond NP. This turned out to be a little bit more finicky than I expected at the start. Okay. Yeah, so recently, total search problems outside of NP have become very popular, and particularly this like range avoidance problem that Oliver Korten has worked a lot on has like had a lot of applications in getting circuit lower bounds. And it's not too hard to see why. So the range avoidance problem is as follows. It's like the inverse of the pigeonhole principle. So you're given a map where the domain is smaller than the range, something like this, and you want to output a hole which is not mapped to by any pigeon. Okay, and so this kind of captures the complexity of finding the truth table of a hard function. you can think of the pigeons as being circuits of, say, polynomial size or some fixed size S, and the holes as being truth tables. And then this range avoidance problem is in a class C, implies that C is not in p-poly. It doesn't have polynomial size circuits. And this is because if you could solve range avoidance, then you could construct the truth table of a hard function efficiently. Okay, so this led to this exciting recent result, which showed lower bounds against the symmetric exponential time class. So this is kind of like the lowest class, or one of the lowest classes down for which we have circuit lower bounds against.
How should we think about size here in range avoidance? I mean, I'm trying to understand, is range avoidance like, I wanted to say that it's total search co-NP problems, or no?
Is
Because
it,
it's sort of, it's
yeah, it should be verifiable with like a universal. Yeah, because you want to check, like, given a whole, check that for every pigeon it doesn't map to it. Yeah. It turns out that if I'm remembering correctly, so you can always collapse it to the sigma classes. So I think co-NP becomes sigma TF sigma 1. Don't completely quote me on that. This is in the original paper.
But here you have an h from 2n to 2n plus 1, but in the example of truth tables,
oh yeah, it could be much larger. Yeah, yeah. So this is, it's like weak pigeonhole. You can,
okay.
Yeah. It's like how in weak pigeonhole you can scale the number of holes. Here it's robust to scaling the number of pigeons.
Okay.
Yeah. And so the weakest class against which we have lower bounds was in this recent paper by Courtney and Picassi, Tony, who showed that avoid is in this linear ordering principal class, which for those of you in proof complexity, this is like the class characterized by like the GTN problem or LOP problem, linear ordering.
Wait, sorry, so
You're given like, oh, sorry. Yep.
No, I think I missed. You said lower bounds against the metric exponential time. What it
So there's something in symmetric exponential time that doesn't have small circuits.
okay.
Yeah.
Okay. And this,
Yeah. The against thing versus
to avoid?
So the way that this result works is by showing that avoid is contained within this class.
Okay.
So avoid's like find a hard truth table. So this class can find a hard truth table. Therefore,
okay. Okay.
Yeah. Okay, and so we can also consider the strong avoid problem, which is like the pigeon version of like weak pigeon. So now the range is only one more than the domain. And this captures the complexity of finding objects with the union bound, roughly. It's the complete problem for the class PEP, and of course, APEP, the class for weak avoid or just avoid, is contained in PEP. So can we get evidence for the hardness of these classes? So here's the TF sigma 2 classes. So avoid is a problem in TF sigma 2. These are the ones that were considered. So PEP, APEP, and linear ordering. So we want to structurally understand how these classes relate. For TFNP, the main technique was proof complexity. Can we use proof complexity here? The question we're asking. So let's try to talk about what this means. Can't be exactly proof complexity because now we're dealing with things in the polynomial hierarchy, but maybe we'll draw some analogies. So our definition of a TFNP characterization was the following. So we need to, in order to generalize this to TF sigma 2 or other things in the polynomial hierarchy, we need to ask, like, what's the proof system for the total function polynomial hierarchy? And is there an analog of the false clause search problem for the polynomial hierarchy? Now we're going to be working with like QBFs or like formulas of higher depth. Yeah, and the reason was that the heart of the connection between proof complexity and TFNP was this false clause search problem, which we're going to develop an analog for. Okay, so a search problem is in TF sigma 2. We'll only talk about TF sigma 2 in this talk, but this generalizes to whatever level you want. So search problems in TF sigma 2, if for every output and every so you want to fix like a yeah, there's like a number in polylog n such that for every output there's a decision tree for every output and extra string z in 0, 1 to the polylog n. There's a decision tree TOZ such that like O is a solution on input X if and only if you can verify it like by this quantifier over decision trees. Just the decision tree analog of like the how you would do it for the polynomial hierarchy. Okay. So what we want to do is encode the totality of this TF sigma 2 problem as an unsatisfiable formula, such that falsified subformulas give you solutions to the total search problem. This is again just mapping to what we did for the false clause search problem. And some definitions: a sigma 2 formula is just going to be an OR of ANDs. A sigma 1.5 formula is an OR of polylog with ANDs. Okay. So we're going to do what I said. We're going to turn this into a unsatisfiable formula. So first we write down that for each solution, we're going to write down that O is a solution. That is, it's this sentence here. We're going to write it down propositionally because we want to talk about propositional proof systems. So we can write down that O is not a solution by putting a negation, bring the negation through like this, turn the existential into a big OR. And now we want to write down that this thing, that O is not a solution given the advice fed on input X. So we take the decision tree, we look at all of the 0 paths, and we take a big OR of them. So it means we take some 0 path in this decision tree. This is polylog depth, so this is a sigma 1.5 formula. And now we get the formula that says that O is not a solution, which I'll denote by FRO. So looks like that. And then to say that R is not total, we just take an AND over all of these. Oh, and the observation is, yeah, that if O is a solution, then this formula is falsified. And yeah, so this is how you write that R is not total. And this brings us to the analog of the false clause search problem, which is called the false formula search problem. You're given as input X, and you want to output the index O such that one of these sub-formulas is falsified. Okay. And so the claim is that TF sigma 2 is exactly the study of this false formula search problem. The proof is just this observation here. It's exactly as we did before. And so the upshot is we only need to consider the false formula search problem. Okay, so now the goal is to get characterizations of TF sigma 2, and in particular to define what even a proof system means in this context. Okay. So we can't just use standard propositional proof systems. And the reason is that the false clause search problem is in TFNP for every unsatisfiable free CNF formula. And there's TF sigma 2 classes, which contain all of TFNP. And so if you had a Cook-Reckhow proof system characterizing one of these TF sigma 2 classes, then you'd be able to prove every unsatisfiable 3CNF formula, and NP is equal to co-NP, which would be not what we think. So it can't be a Cook-Reckhow system. So what can it be? Like, what should it turn into? Okay, so proofs of characterizations proceed in like kind of the following two steps. So first, you show that roughly that the proof system can reduce the formula. So if you're trying to prove F, prove an unsatisfiable formula F with a proof system which is characterized by class C with complete problem false formula of G, then you want to first prove, so we know that the false formula for F reduces to the false formula for G, and you want to prove this reduction in the proof system. You want to reduce F to G, and then you want to prove G. This is roughly the two steps. Surprisingly, we show that really this reduction is the only thing that fails. We can always just use Cook-Reckhow proof systems for the second thing. So you should think of G as being like encoding the totality of some TF sigma 2 problem, and Cook-Reckhow proof systems can do this. So we're just going to take standard Cook-Reckhow proof systems and augment them with basically a weakening rule that will allow us to do the first thing, allow us to do the reductions in the first part. Okay, so I'll talk a little bit more about what reductions mean, and this will give us our definition of a proof system. Okay, so let's fix two sigma 2 TF sigma 2 problems, or I guess sigma 1.5 unsatisfiable formulas. This is what we're proving. This is like the analog of a CNF formula in this world. And we're going to look at a decision tree reduction from the false formula search problem for F to G. So we have a decision tree turning inputs to F into inputs to G, then another one turning solutions back. So that is this implication holds. This is just the definition of reduction. And we're going to ask what this means propositionally. So this means that if we falsified the Oth subformula of G and then we looked at the decision tree GO and followed the path P here, and it was labeled by something O star, then the O starth subformula of F would be falsified. This is just the correctness of reduction. So in particular, we have this implication. So we can reverse this implication and get that that if you falsify the O starth subformula of F, and you follow the path, then the Oth subformula of G, after you stick in the decision trees for each variable, and you follow path P, is going to be falsified, or is going to be implied by this. Okay, so what this means is, I'm writing this so that you can think about this as like a weakening step in resolution, essentially. But now we're dealing with stronger formulas. So we have this implication that this subformula of F implies this subformula of G after you've composed it with the reduction. So in particular, this means that this subformula over here is a sigma 2 weakening of this subformula of F. So remember that a weakening of a clause, you're just allowed to like throw in more literals. It's just more satisfiable. Similarly, you could talk about weakenings of, say, sigma 2 formulas where you derive anything, like the sigma 2 weakening of formula A is any formula B such that A implies B. And we're also going to need the definition of a reduced formula. This is just the CNF formula you get after plugging in the reduction. So this is what you do is you start off with your formula, or not CNF formula, but sigma 2 formula. You start off with your formula G. You plug in these little decision trees for each variable that you then propositionalize that. And then you take an and over the negation of each of the paths. So this is just what you get after propositionalizing the fact that this is a valid reduction. A little bit definition heavy. Does that make sense? Is there questions? This is not super important to understand. The main thing is just that like the weakening thing is important and the fact that you can sort of propositionalize a reduction. So if you reduce the false formula search problem for F to G, then this is sort of like the formula you get out of sticking the reduction into the form. Okay, and this is again encoded as a sigma 1.5 formula. You can do that. It's just the fact that it's loaded up decision trees. Okay, so note that this weakening rule is not polynomial time verifiable because, for example, B could be true. So if you could always take any, if you could check that A implies B, or B is true, then this is the same as checking whether a CNF formula is inside, or a DNF is tautological. So this means that you're not going to get a Cook-Reichenbach proof system out of this. But again, our goal is to come up with a proof system which, the definition of a proof system which characterizes GF sigma 2 problems. A proof, again, is just going to be first you run the reduction, then you prove the complete problem. So running the reduction or deducing the reduced problem, this needs sigma 2 weakening. And the second one, you can just use a Cook-Reichenbach proof system. Okay, so that leads us to our definition of a sigma 2 proof system, which is just, so we're proving now sigma 1.5 formulas or sigma 2 formulas. So like this is ors of ands of ors. And a proof in this, like a proof system for this setting is a standard Cook-Reichenbach proof system, plus you're allowed to do this weakening rule at the start. So first, so a proof is in particular a proof of a formula F is a pair H and pi. So pi is a proof, H is another formula, such that H is like an and over a bunch of these HIs, and each of these HIs is a sigma 2 weakening of one of the subformulas of F. So basically, you can think about it for, like, maybe it's easier to think about for CNF formulas first. So like the corresponding thing for CNF formulas, I'd start with a CNF formula F. I'd take each of its clauses and weaken them to something. This would give me H, and then I would prove H. So here we're just doing it with, now there's one more depth to our formula. So first I take each subformula, which is like a D and F, and I weaken each one. And then I get a new formula H, and then I prove H in a propositional proof system.
So for resolution, it wouldn't help if you did that, but in other proof systems you can do.
Exactly.
But is the fact that you're working only on weakenings of original things make it easy to? Wait, are these? No, this that's not easy to verify either. But it's somehow
no. So this is not verifiable.
Not verifiable.
It's verifiable like by a sigma
By
2
sigma 2.
thing. Yeah, just because of this first step. Yeah. Yeah, so question is, this is a weird definition of a proof system. We were hoping to get like these QBF proof systems out of this. We weren't able to. That's an open question. Can you show that this is somehow like equivalent to like some sort of QBF proof system? Because then that would be nice. It'd bring together like two pieces of literature. But how do we know that this is the right definition if we got something weird out of it? Well, we got this. So before I mentioned that there's this like, there's this result showing that like every TFNP class has a corresponding proof system. We get the same thing for TF sigma I for all I. So this kind of shows that this is the right definition of a proof system for the total function polynomial hierarchy. We get that each class has a corresponding proof system, and vice versa. Each proof system that proves its own reflection principle, now about sigma D formulas, has its own class. Here were the old classes that we looked at, or the people had defined, and using proof complexity, we defined a bunch of other classes in TF sigma 2, and we gave characterizations for a bunch of them. So these are, we defined like a sigma 2 version of PLS. These are all sigma 2 proof systems, to be clear. So they have the sigma 2 weakening thing. So there's like a PLS, like a sigma 2 version of PLS that gives you res polylog, for example. These actually, so you mentioned the game induction principles before. So like you can think the unherbrandized version of game induction is like basically this. Is the complete problem for this. So you can give also TF sigma D class that corresponds to like AC0, depth D AC0 fragments. And these game induction principles for D. The most interesting characterization, in my opinion, here is this is that the strong range avoidance problem is equivalent to sigma 2 Schiraldi-Adams. Yeah, maybe I can show you that in the last couple of minutes. So remember, strong avoid was the problem. It's like reverse pigeonhole. You're given a map from n things to n+1 things. You want to find something that isn't mapped. Then I want to show you that this is exactly what you can prove in Schiraldi-Adams with sigma 2 weakening. And then a great question is to do just a void. So now the range is larger. It's like twice the domain. And it should be doable. It's just that like the things that I thought should work don't exactly work. But that would be very nice because a void has all these really nice connections to like circle around. So a conjunct will encode as a polynomial and just still call it a conjunct. Probably familiar with this. Conical juntas are non-negative sums of conjuncts. And then Schiraldi-Adams proof of the fact that a set of polynomial inequalities has no common 0-1 solution is this thing. So you take each of these polynomials, you multiply it by a conical junta, then you're allowed to add in one more conical junta. and we're going to work over a multilinear arithmetic. So x squared is always equal to x. This has the same effect as restricting to 0, 1 points. This is sound because conical juntas are non-negative over 0, 1 assignments. And if there was an assignment which satisfied all these polynomials simultaneously, then it would set this thing to greater than or equal to 0, right? Because conical juntas are non-negative, these PIs are non-negative, you get a non-negative value. So you can only derive -1 if the polynomials you began with had no common solution. The complexity is logarithmic in the number of monomials plus the degree. Yeah, and the theorem that we're going to prove is that there's a polylog complexity Shirley-Adams proof of a formula if and only if the false formula problem is reducible to strong avoid. So remember that strong avoid was, just given a map where the range is 1 more than the domain, and you want to output a whole that's not mapped. We can encode this propositionally as the following unsatisfiable formula. This just says we have one of these for each whole, and it just says that some pigeon maps to me. This is unsatisfiable because there's more pigeons. I mean, more holes than there is pigeons. And then you can encode this as a polynomial. So we're just gonna, each of these is a small polylog width term. So if you have an OR of terms, you can encode that as saying the sum of the terms has to be at least 1. So you get this encoding and the 1 is cut off. So it's pretty simple to see that Shirley-Adams can prove strong avoid. You just sum up the axioms. So you have 1 axiom per hole. You sum up over all the holes. You flip the sum here. And now we're summing up over all the pigeons, summing up over the holes. This thing sums to 1 because it's basically like summing over all paths in decision tree. The -1 here becomes 2 to the n. I'm just bringing it out of there. So we get this thing becomes 1. So 2 to the n minus 1 minus 2 to the n is -1. Very simple proof. You didn't even have to use any of your conical juntas or anything like that. You could also prove using the same sort of idea any reduction to strong avoid, like you can prove the reduced formula. First you derive the reduced formula using sigma 2 weakening, and then you sum up over all the axes. Yeah, so you can prove if you can reduce to strong avoid, you can prove the corresponding formula in Shirley-Adams. So first you weaken to the reduced formula, then you prove the reduced formula in Shirley-Adams. Okay, so the other direction is about 5 minutes, and it's much more interesting. Okay, so if you have a Shirley-Adams proof of a formula, then you can construct a reduction to strong avoid. We'll study the equivalent problem called unmetered source of DAG, which says that every DAG has, roughly every DAG has a source, kind of, but unmetered means you're allowed to actually point backwards, kind of. So the input is a set of nodes. It's similar to iteration. The input is a set of nodes. The domain is going to specify vertices. The range is going to specify edges. So, or like the function specifies edges. So we call this the successor function. So if you take its input a vertex, it outputs the vertex it should point to. And you want to output either 1 if 1's not a sinc. You're looking for a source. This is like a universally quantified thing. So 1 is not a source if either, sinc if either 1 points to something, so it doesn't self-loop, or nothing points to 1. And second, so we want basically the first thing is just saying 1 has to be a sinc. And that means that somewhere else in the graph there has to be a source. The second thing just says find a source. So in this thing, 6 is the source. This is equivalent to strong avoid. It's pretty easy to see. We'll create 1 pigeon for each vertex and 1 hole for each vertex plus an extra hole star. We're going to map 1 to the special star thing, and everything else just maps to the corresponding guy. And you can see that 6 becomes not a solution. Basically, mapping 1 to star is saying that 1 has to self-loop. Okay, so we can study this unmetered source of DAG. If we have a proof of this formula in Shirali atoms, of F in Shirali atoms, looks like something like this. I'm just going to move the 1 to the left-hand side. And so we're going to construct an instance of unmetered source of DAG from the Shirali atoms proof. Yeah, so we're going to introduce 1 vertex per monomial. We're going to group the vertices based on which group here they came from. Either they came from one of these DIs, which is a DNF, or from the J, something like this. And we want that a vertex belonging to DI as a source. If we have a source in like one of these DIs, then the DNF corresponding, like the DNF DI is false. So we can define edges. This is similar sort of to the Shirali atoms characterization of PPADS, if you've seen that, but also sort of different. Because the whole proof sums to 0, monomials occur in plus minus 1 pairs. Yeah. And so for monomials with a negative coefficient, we're going to match them to their positive counterpart, right? Everything sums up to 0. So for every positive monomial, there has to be a negative occurrence of it. So we match them up like this. Oh, and if a monomial is 0 under the assignment, we'll just self-loop it. Otherwise, we'll match it to its corresponding guy. These each occur in like different groups because you're never going to get like in one of these DI, like one of these groups here, you're never going to get monomial occurring positively and negatively because just 0. So we can assume that they occur in different groups. They go across like that. And this causes 1 to become the designated sinc. So -1 points to 1. 1's going to end up self-looping. And we'll put edges for positive monomials within. And what we want is that, yeah, if the ith DNF is false, then we have a source in DI. So conversely, sort of if the DNF is true, then at least one of its terms is true. So if we have DNF with 3 monomials, we have a picture like this. So the DNF is encoded as M1 plus M2 plus M3 minus 1. So M1, M2, M3 are the terms of the DNF. Because we matched negative monomials to positive monomials, like M1 has, like each of these MIs has an incoming edge. And because we matched, yeah, negative to positive, -1 has an outgoing edge. So right now, sort of before we add any edges from the positive monomials to anywhere, -1 is like a candidate source. This is kind of the heart of the proof here. So what we're going to do essentially is that each of these monomials or terms of the DNF are going to query the variables that occur in them and say, okay, if this monomial is 0, so to satisfy the DNF, we have to satisfy one of its terms. So for each term, we're going to query all the variables in that term. We'll point it to the corresponding -1 if the term is 1, meaning the DNF is satisfied, and otherwise we'll self-loop it. So here, let's suppose that M1 is false, so we'll loop it to itself. Maybe M2 is also false, we'll loop it to itself, but maybe M3 was true, and so it points to -1. This means that -1 is no longer a sink, and so we don't get a solution there. This is kind of the heart of the characterization. Now we just have to deal with the fact that our DNF is not so simple. Rather than being a sum of monomials, it can be terms times juntas, but this is pretty straightforward. Basically, all we do, so -1 is a source if and only if DI is false. So if DI is the OR of terms, then we use the fact that the number that in the conjunction corresponding to the term, the number of positive monomials is greater than the number of negative monomials. So we can just fix a matching on them. And then it kind of reduces to the previous case. So we choose 1 to act as like the MJ from before, like MI, 1 positive monomial, and then we fix a matching between the remaining things. What we're crucially using here is the fact that each term is like polylog width, so we can query it all and we can learn information about it. And for the full generalization, again, with a junta, the number of positive monomials is at least the number of negative monomials. You pick 1 negative monomial to play the role of -1, and you fix a matching kind of between the rest. And you can query. That's the same. Okay, so I think that's about time, and this basically completes the proof. Hopefully that gives you some idea of how to do these characterizations for sigma 2 proof systems.
Okay. Thank you.
Any questions?
Maybe relate to the first part where we were asking for a natural TFNP class that will be in a natural proof system. Is the converse known or expected to be true for every natural proof system? Get natural.
Oh, that's a I don't know how you would define like a natural TFNP.
It's related to some mathematical principle.
Good question. I would imagine there the answer feels like it should probably be yes, because if you're defining a proof system, you're somehow defining some sort of type of reasoning, which is probably captured by some mathematical principle, which then that principle probably gives you a natural thing. But I've never really thought about a converse to it. Any other questions?
So thanks again.